black holes are invisible. But when two orbit each other, they become some of the most powerful objects in the universe. As they spiral inward, they accelerate. Acceleration of massive objects disturbs spacetime itself. According to Einstein's theory of general relativity, accelerating mass produces ripples in spacetime. These ripples are gravitational waves. Unlike light, gravitational waves are not blocked by dust or gas. They travel through the universe almost undisturbed. When two black holes merge, they release more energy in a fraction of a second than all stars in the observable universe combined, in gravitational radiation. These waves stretch and compress spacetime as they pass. But by the time they reach Earth, their distortion is incredibly small. Detecting them requires extraordinary precision. In 2015, ground-based detectors confirmed gravitational waves for the first time. But those detectors are limited. They detect high-frequency waves from stellar mass black holes. Supermassive black holes produce lower-frequency waves. These waves are too large to detect on Earth. Earth itself vibrates. Seismic noise interferes. To hear deeper cosmic events, detectors must leave the planet. That is where LISA enters. Low-frequency gravitational waves have wavelengths millions of kilometers long. To measure them, detectors must be separated by vast distances. On Earth, this is impossible. In space, it becomes achievable. LISA will consist of 3 spacecraft arranged in a triangle, each separated by approximately 2.5 million kilometers. Laser beams will travel between them. As gravitational waves pass, distances between spacecraft change slightly. These changes are smaller than the width of an atom. But lasers can detect them. Space becomes the laboratory. Spacetime becomes the signal. LISA does not observe light. It listens to geometry. Gravitational waves carry information about black hole masses, spin, orbital dynamics, merger timing. Unlike telescopes that see electromagnetic radiation, LISA measures distortion. This is not imaging. It is listening. The universe has always been vibrating. Humanity is building the instrument to hear it. LISA will not orbit Earth. It will orbit the Sun. The 3 spacecraft will trail Earth in a heliocentric orbit, maintaining a triangular formation. Each side of the triangle will measure approximately 2.5 million kilometers. That is more than 6 times the distance from Earth to the Moon. The formation will slowly rotate as it orbits the Sun. This rotation allows LISA to scan different parts of the sky. But maintaining this geometry is not simple. There are no rigid arms connecting the spacecraft. They are free-floating, separated by vast distances. Their relative positions must be measured with extraordinary precision. Even tiny perturbations from solar radiation pressure, micrometeoroids, or thermal expansion could introduce noise. The spacecraft do not physically connect. The triangle exists through measurement. At the heart of LISA lies laser interferometry. Each spacecraft sends and receives laser beams to and from the other 2. When a gravitational wave passes, it stretches one arm of the triangle and compresses another. The change is minuscule. The distance variation may be on the order of picometers, smaller than atomic dimensions. The interferometer measures phase shifts in the laser light. By comparing the returning beam with a reference beam, tiny length changes can be detected. This technique was proven in space by the LISA Pathfinder mission. Pathfinder demonstrated that drag-free control and interferometric precision are achievable. But scaling to millions of kilometers introduces new complexity. Time delays between spacecraft must be precisely calibrated. Signal timing must be synchronized. The laser beams themselves diverge slightly over long distances. Precision is everything. To measure spacetime distortion, spacecraft themselves must not introduce motion. Each LISA spacecraft contains a freely floating test mass inside. This test mass is shielded from external forces. The spacecraft surrounds the mass but does not touch it. If solar radiation pushes the spacecraft, microthrusters adjust its position to keep it centered around the test mass. This system is called drag-free control. The test mass follows pure gravitational motion. The spacecraft follows the test mass. This reduces non-gravitational noise. Without drag-free control, solar pressure would overwhelm the signal. Gravitational waves are subtle. Engineering must be quieter than spacetime itself. Detecting gravitational waves requires eliminating every possible source of disturbance. Thermal expansion of components must be minimized. Laser frequency noise must be stabilized. Clock synchronization across millions of kilometers must be maintained. Time delay interferometry is used to mathematically cancel noise. Signals from different arms are combined in specific ways to subtract laser noise. This processing occurs after the data are transmitted to Earth. Unlike ground detectors, LISA must contend with cosmic rays and deep space radiation. Every component must function autonomously for years. The mission will not be adjusted daily from Earth. It must operate with stability across astronomical timescales. Noise is the enemy. Silence is engineered. When galaxies merge, their central black holes eventually meet. These are not stellar mass objects. They contain millions or billions of times the mass of the Sun. As they orbit each other, they emit low-frequency gravitational waves. These waves take years to complete a single oscillation. Ground detectors cannot hear them, but LISA can. LISA will observe these mergers long before the final collision. It may detect systems years before they merge. That advance warning allows telescopes to prepare. For the first time, gravitational wave astronomy and electromagnetic astronomy can be synchronized. We will not only see galaxies merge, we will hear them before they collide. These events shape galactic evolution. Understanding them reveals how structure in the universe grows. Not all signals will be dramatic collisions. The Milky Way contains thousands of compact binary systems. White dwarfs orbiting each other emit steady gravitational waves. LISA will detect a background hum from these systems. It will create a gravitational map of compact objects in our galaxy. Some binaries will merge quietly. Others will transfer mass. LISA will catalog them. Unlike electromagnetic surveys that depend on brightness, gravitational waves depend on mass and motion. They reveal systems hidden by dust. The galaxy will not be silent. It will hum. Perhaps the most ambitious goal is detecting primordial gravitational waves. In the earliest fractions of a second after the Big Bang, spacetime itself may have fluctuated. Those fluctuations would have produced gravitational radiation. Unlike light, gravitational waves travel largely unimpeded through matter. If primordial waves exist in LISA's frequency band, they would carry information from epochs otherwise inaccessible. This would allow cosmologists to probe physics at energy scales beyond particle accelerators. Such detection would test inflationary models. It could reveal symmetry-breaking events in the early universe. This is not guaranteed, but if present, the signal would be profound. It would be the earliest sound ever heard. Astronomy began with light, visible light, then radio, X-ray, infrared, gamma ray. Each band revealed a new universe. Gravitational waves add another sense. They do not show images. They reveal motion in geometry. They allow us to measure mass directly. They are unaffected by dust. They reach us from hidden regions. LISA extends our hearing into frequencies never before accessed. The universe has always vibrated. We are building the instrument to listen, not just to events, but to structure, not just to collisions, but to cosmic history.